Okay, great. Okay, hello everyone again. So I'm here with my colleague at the time, Tatsu Ito, who was at Brookhaven National Laboratory in our group, and he really kind of closed the deal on making the FDG. So I titled the talk Working Against Time, because we basically had to do all of this development and get it down to the University of Pennsylvania, where the camera was. So what we're talking about here is to be able to pinpoint where glucose metabolism is occurring in the brain. As I told in my opening remarks a little earlier, this is a rat brain. This little red spot occurred because they were just tweaking one whisker of the rat. So you can see if you could actually pinpoint where metabolism is occurring, it would be extremely powerful. So this was done in an animal. This was done on a slice. And what their vision was to be able to do that in a living human being. And so that's why they had come to Brookhaven. So this is a picture of Louis Sokoloff, and this is Martin Rivich. And just to go over this one more time so you can see the molecules, this is the glucose molecule. We're talking about position 2 here. It has a hydroxyl group on it in glucose. In deoxyglucose, it has a hydrogen atom. So you have a blood-brain barrier, and it's a barrier that allows things in like nutrients, like glucose. So your brain uses glucose almost entirely as an energy source. So if you can pinpoint where glucose metabolism is occurring, you have a very powerful method. So in the brain, there's an enzyme hexokinase, and it phosphorylates the glucose inside of the cell. It forms glucose 6-phosphate, which is charged. But with glucose, it goes on to other products and generates energy, and you have small molecules moving in and out of the brain. With deoxyglucose, it undergoes the first step of glycolysis. You get the charged molecule, as Alex nicely described this morning, that stays in the cell. So imagine you're trying to take a picture and things are moving in and out of the picture. You don't get a good picture. You get a fuzzy picture. You really don't know what you're taking a picture of. However, if you use this molecule, it becomes stuck there and you get a nice picture. So our challenge was to label this molecule with an isotope that retained these nice properties, but also could be used in humans. And so this is at a group around the same time period. And so we had a lot of expertise on cyclotrons, on nuclear and radiochemistry, on isotopes. Let me just name a few of the people at the time. Dick Lambrecht, the nuclear and radiochemist, a lot of expertise on cyclotrons and targets. We had Brian Gallagher, who's a biochemical pharmacologist. And when we decided we needed to get into looking at life, chemistry and life, we hired Brian. Dave Chrisman taught me a huge amount about isotopes and handling isotopes. We had David Schleier at the time, who's still here, who's an expert on cyclotrons and radioisotopes, and now on imaging instruments. We had Bob McGregor. Bob actually put the carbon-11, which has a 20-minute half-life, on the deoxyglucose molecule. And that wasn't what we needed to send it to Philadelphia, but we used it a huge amount here at Brookhaven because we could do serial studies in the same person. Bob died a couple of years ago. Al Wolf, the leader of the group, Al had tremendous experience in hot atom chemistry and isotopes and envisioned to use these short-lived isotopes in humans. Al, I learned a lot from Al. Al had two pieces of really useful information. He said, if you're hiring people, you should hire the smartest people you can, even if they're smarter than you, hire them anyway. So that was a really good piece of information. He also said, don't put all your eggs in one basket. So, if you're doing a lot of different kinds of things, it's a good thing. One of them may really come in big. And at the time, we were doing a lot of different things at the time. I remember Dave Schleier was working on coal, and we're still finding pieces of coal around the lab. So we were doing a lot of different things. In addition, we were trying to make these isotopes sterile so that we could inject them in people. Karen Karlstrom is here. She took that on as a cause to make these products. So not only you start with a cyclotron, you have to end up with something that can go into people's veins. And we had Chin Shu at the time, Dave Lloyd, me, Hernan Vera-Ruiz, Betty Crawford, Toshi Hara. We had a really kind of an eclectic group at the time. And we also had a cyclotron. This is Ron Finn, who was there at the time. This was our 60-inch cyclotron. We decommissioned it a couple of years ago. This was kind of a melancholy experience because for many of us, this was our first cyclotron. And so it had to go. And well, most of it went. It was too heavy to decommission most of it. But we had a machine that produced deuterons and protons and helium-3 and alpha particles. So we could do a lot with nuclear reactions. And so these were the isotopes that we were expert at. Carbon-11, which is still our favorite, 20-minute half-life, and fluorine-18, which has 110-minute half-life. And now we're also using nitrogen-13 a lot because we have this plant program and plants use nitrogen. But this required the development of rapid synthetic methods. And so the first thing that we did when we started to go through this and figure out where to put the fluorine is we started looking at the literature, and there these two biochemists, Salz and Crane at the Washington University, had taken the glucose molecule. This was like 20 years before 1974. And they had gone around the molecule, successfully removed different hydroxyl groups to see what was really important for the molecule to be a substrate for hexokinase. And they found that the only one that you could remove and still have the hexokinase activity was at C2. But they also found that it was not a substrate for the next step, and that it would not undergo active transport, and that also becomes important. But they had this statement: the removal of the hydroxyl on C2 isolates the hexokinase reaction. So that was really pretty prophetic statement. So what we had here then is these two molecules. This was our goal molecule. This was the one that was used by Sokolov. And we wanted to put a fluorine-18 there. Fluorine-18 has a 110-minute half-life, so we figured we had a fighting chance of being able to make enough of it. And we had an airport down the road to send it to Philadelphia. And this is kind of where Tatsuo Ito came in. And as Lou Sokolov said, the first thing they wanted us to do was make sure, if we're going to invest the time to make a lot of a fluorine-18 radio tracer, that we should do it with C14 first, make sure the fluorine doesn't do something unpredicted. So we, and this was actually a literature method, but you could add fluorine gas. Now fluorine is extremely reactive. It's probably one of the most, if not the most, reactive elements. So it's kind of hard to handle, but there was some work in the literature going on at the time. If you diluted it up and cooled it down, you could kind of tame it. And so we added it to a double bond of the C14 labeled molecule and made, after GC separation and hydrolysis, made the C14 version. You saw these earlier in Lou Sokolov's video. It behaved just like the oxyglucose. So we had a reason to go on with this. Now the next thing was to make enough elemental fluorine with F18 on it. And to make F18, we started with neon gas. So if you bombard neon gas with deuterons, an alpha particle is produced, and fluorine-18 is produced. And if you put a tiny little bit of fluorine gas in there, it exchanges off the wall, and you get molecular fluorine labeled with F18. And you do it in this as a target. So this is it's just a little target. It's about, the target is called neon, but this is a nickel chamber because we had to use nickel for its inertness to the fluorine. All of this brass hardware is cooling because we're putting a beam of around 20 million electron volt deuterons through this thin window into this neon gas, which is pressurized to about 300 psi. And that's where the nuclear reaction occurs. And you bombard for about 2 hours to get a large amount of elemental fluorine labeled with fluorine-18. The inside of the target was very important. We spent a huge amount of time on these targets, washing them, polishing them. And if you polish to a mirror surface, you got a really nice yield. This is after the beam. You can see there's a lot of heat and everything dissipated in that target. And this was the reaction. Elemental fluorine adds to this double bond, and it adds from two faces of the molecule, so you get a 4-to-1 mixture, 4 in favor of the right configuration. You hydrolyze it, in the process losing half of the fluorine 18. So this gave us enough of this molecule to put on the plane and send it to the group in Philadelphia. Yields were kind of low, but we made it, and there was enough to demonstrate proof of principle. And so these are some early pictures. This is Tatsu Ito, Chunyan Wan, and Al Wolf in front of the hood where they made the fluorodeoxyglucose over in building 901. This is Tatsu delivering the fluorine 18 to Pennsylvania, and Vito Casella, who worked on the F-18 target. And this is in the room with Dave Kuhl's Mark IV camera. So this was this early tomograph that could make a cross-sectional image of a living human brain. This is a volunteer, was a medical student. And in quantifying this isotope uptake, you can actually measure the rate of glucose metabolism per 100 milliliters of brain per minute. This is Joel Greenberg doing blood sampling, Martin Rivich. And then if you look at the next slide, this is discussing results. This is a picture of David Kuhl, Martin, Michael Phelps, who had joined the group at that time. And these were the first images. They looked great to us at the time. They look pretty blurry, blurry right now, but we were so pleased. This is gray matter, which shows dark and slices of the brain, and white matter, and they actually calculated the rate of glucose metabolism in the visual cortex is 10 milligrams per 100 grams of brain per minute, and in white matter, which we know is about 4 times less metabolically active, as 3.4. And so this kind of told us this was going to be pretty useful. And at the time, at the same scan, this person, we were just looking at his brain, but Abbas Alavi, who was part of this first team, I think this was your idea, right, Abbas, to put the person through a rectilinear scanner and see what's going on in the whole body. We've got the person labeled, and you could see the FDGs in the brain because the brain's using sugar. It's also in the heart. Normally the heart's using fatty acids, but we frequently see FDG taken up and phosphorylated by the heart. We also see the bladder. Now this is actually something very cool because it turns out that you need the hydroxyl on the 2-carbon in order for the body to transport glucose back up and recycle it. So normally you would not see glucose or sugar in urine. You see it here. The body recognizes that this isn't really glucose itself. It uses an active transport mechanism and secretes it. But what's very nice about this is the body background is pretty low. And around this same time, Prantika Sam, who passed away last year in our group, this started to look at glucose uptake in tumors and found that glucose, or FDG, was very rapidly taken up by tumors. And this suggested that it would be very useful for looking at tumors in the human body. And this is a slide from Mike Phelps at UCLA. This is a whole body image. It shows you why this is so useful. You can see, and this is a later PET scan, you can see much better delineation. You can see the woman's brain. You can see muscles here, use sugar. You can see her heart. You can see the bladder again because of this active transport thing. She had ovarian cancer and lung metastases. And you could see this, and you can just see these things very clearly. And now oncologists use this just to look at where the tumor is, how active is it, and is it responding to chemotherapy, because you can do serial scans. So this showed us that we really needed a better way to make more FDG. And so at that time, Thomas Ruth, who's now at Triumph, was in the laboratory, and we had done the group did a lot of just very basic studies of particle energy and yield, just to determine how do you make the most ice, how do you make the most out of your cyclotron beam. So this is particle energy and MeV, and we had at this time this variable energy cyclotron, and we also used the tandem Van de Graaff for some of these studies. And this is the yield, and this was the neon D-alpha reaction. You can see, you use this to tell, what energy to pick for doing the bombardment, but you can see this kind of plateaus around, around 15, 20 MeV. And look at the yield for the O18 PN reaction. You bombard O18 with protons, and you get lots of F18, huge amounts, and you get it at fairly low energy. So this was really, really very nice. It gives it as fluoride ion, which is a nice thing to work with. We made small, this was done by Bruce Whelan in our group at the time, made very small volume water targets. So you'd use 95% enriched water, 1 cc, spread it out in a little window, lots of cooling because you're putting a lot of energy in, and could produce very large quantities of F18 fluoride ion. So this underpins the synthesis of FDG from fluoride, which was done by Kurt Hamacher at Jülich. Everyone was trying to develop a rapid way of making FDG from fluoride, including us, and these folks accomplished it, did a really nice job. And that stimulated a lot of things, including the development of black boxes for producing F18 FDG. So this was the synthesis of Hamacher, very simple. Everyone was kicking themselves when they saw how nice and simple this reaction was. This produced large amounts. It was very amenable to automation. And these were some of the black boxes that are available now. People can buy a black box where you put fluorine 18 in as fluoride in one part of the box and get FDG out of the other part of the box, just computer controlled. Tatsu Ito first suggested that this is what we needed at a meeting in 1980. Dave Alexoff built one of the first boxes in 1986 here at Brookhaven. We used for many, many years. I don't know how many years this was. 15 years this thing just cranked out FDG. Then we tumbled to buying it. For $300, you can dial an 800 number and get it, which was, so we do that now. But companies now sell these black boxes, and one of the latest things that's being developed at UCLA is to use microfluidics and make chemistry on a chip. And so now there are these PET radiopharmacies. About 3 different companies just set up a cyclotron, a radiopharmacist, and a black box, and make FDG to send to regional centers so that they could send it to hospitals that don't have a chemistry group and don't have a cyclotron. So this is a network of one of these companies, PetNet. It just makes this and just puts it in, makes a huge amount early in the morning and just sends it out to hospitals basically for cancer scanning. And if you want to look at, say, the number of just PET scanners without chemists that just can dial the 800 number and get the FDG, this is a map this is kind of the landscape for that. So if you look at publications, there were not many publications when we first started. Early synthesis in the mid 70s, synthesis from fluoride in 1986, and then people started using it, started looking pretty useful for neuroscience, for cancer, and commercial PET scanners came in around the year 2000. Reimbursement came in around then, so that people could use this and get reimbursed for and use these for diagnosis. This was part of a healthcare HCFA, some act signed by President Clinton, pushed by Michael Phelps, and Senator Ted Stevens really was a proponent of PET. He pushed the passage of a law so that this could be used, and then this has grown exponentially in terms of its use as a research tool and for clinical diagnosis. And so what has happened in the last several years is, as part of not putting all the eggs in one basket, Richard Ferrari in our group was very interested in using these short-lived isotopes for plants, for energy and environment research, because you imagine the cyclotron will directly produce carbon dioxide, which is used by plants. You can make all of the small molecules, you can make more complex molecules. And he said, well, why can't we just use FDG? Give it to the plant, see if it makes the plant make cellulose. And the plant should, in principle, make cellulose because it's a 1,4 polymer. And he found, indeed, you could administer FDG to plants and get cellulose. And so the Department of Energy has reoriented our program from medicine to energy and environment. And so we are now making complex radiotracers to give to plants to look at signaling in plants. And this is all to understand more what's going on in the whole plant. Plants have been studied sort of microscopically, where you'd study them at very, you'd extract the plants, you'd look at them with a confocal microscope. This way you can actually look at what's going on in the whole plant, just like you look at what's going on in the whole human. So this is kind of my last slide. I think this is my last slide. This just kind of traces our work at Brookhaven here. One of the very first predecessors of the ring PET scanner was developed by a man named James Robertson, who was in the medical department at the time in 1960. We developed a lot of the gas targets, the targetry for gas, for making carbon-11. In the early 70s, I've talked about FDG. Gene Logan and our group developed ways of extracting rates out of images, getting numbers of receptors and enzymes. We have a very active program that was started by Nora Volkoff on looking at drug addiction. She'll talk more about it. And then more recently, the group has branched with Dave Schleier and Paul Vasca and Craig Woody in physics, and the instrumentation vision have developed a really neat little PET scanner that fits on the head of an awake rat, so that you could look at brain chemistry and behavior at the same time. So they're doing, in fact, one of the most recent things is develop a plant scanner that can translate up and down the stem of a grass plant. And Anat Began in our group is now looking at estrogen metabolism. We have a really neat tracer for looking at the enzyme that converts testosterone to estrogen. And we're making more complex molecules to look at plant signaling. Richard made the first complex molecule to study plants, methyl jasmonate. We recently developed a synthesis with Alicia Reed, who's at Medgar Evers College, made C11-auxin, which is the plant hormone that makes the plant bend toward light. And this is an example of whole plant imaging. So that's become a really nice part of our whole effort here at Brookhaven. And this is our group. Here, this is our extended group. Our group gets very large in the summertime because we have so many students. And we cover a lot of disciplines. A lot of us are chemists, but we had psychologists in the group. We have pharmacologists in the group, physicists, engineers, physicians, nurses. What have I forgotten? Anyway, we cover a lot of disciplines here. Our support, we've had enduring support from starting with the atomic energy and up to now with the biological and environmental research. We've had support from NIH. We have a partnership with Stony Brook University, and we also do work with the pharmaceutical industry. So I think this is it for me. Thank you very much for all being here.
Let's leave it up for just a minute. If there are any questions before we move on, I thought I'd give you a chance before we go to the next speaker. Events of the past, or how do you fly F-18 on an airplane?
You said initially it took 20 minutes for the chemistry.
No, it took, I think, about 2 hours, right? About 2 hours,
But
yeah.
I say, while she's answering that question, Tatsuo Ito is here. Tatsuo, stand up.
There, yes.
From Japan to join us for the day.
Thank you very much for the invitation and for such exciting ceremony. I'm very happy to that I had been engaged to that kind of the teamwork Thank you very much.
Good. So he had to make that work. How do you get the synthesis done in
How long does it take today?
How long does it? I think it's probably about a half hour in or the time to make a phone call, which is what we do now. But yeah, this thing is it progressed very rapidly. I think when something looks useful, everybody really starts leaning into it, and a lot of progress was made. And then having these regional centers made it available to huge numbers of patients.
So when we transport to Brookhaven to the Philadelphia, it's including the synthesis time, just one half-life of the protein-18. It's about 2 hours.
You had to have the plane running on the airplane.
So in the afternoon, some arrived at some airport in Philadelphia. They did the crew, the secretary, they prepared the brand new 8-inch camera. So she drive to airport. She drive to the airport to hospital. It's very fastly. It's about 15 minutes. Yeah, this is so quiet. She knows it's some way of that some empty road.
I spent a lot of time in Philadelphia. That's not a 15-minute drive. So, Camaro must have done well.
So I can add to that, when we started to make carbon-11 deoxyglucose, we had to measure this thing called a lump constant, which is a ratio or a constant that you use to take into account the differences between deoxyglucose and glucose. So we did those measurements. So what they did have to do is sample across the brain, and we did those studies. We made the C11 deoxyglucose here. We had a helicopter sitting right out by the building that took it to Stony Brook where we did the sampling. So that took like about 20 people to do that study. That got it. We were able to transport carbon-11 to Stony Brook. So it was pretty remarkable. But we did need a helicopter that sat in the field, and it had to be jump-started by a little Volkswagen Beetle. So, you want to move on?
Unless there are other questions.
We didn't have a scanner here. They had the tomograph. So it was right at the beginning of scanners, of cameras. So they had the camera there, all set up in a medical setting, and we had the chemistry. So that was the reason. Otherwise, we would have put C11 on it and done it here.
There had been some early work on predecessors to PET scanners here at Brookhaven, but the best scanner available at the time was at the University of Pennsylvania. There was still in a period when they were trying to figure out how to make a scanner, putting together the pieces so they could get accurate quantitative scanning for PET imaging. Okay, so thank you very much, Joanna. And